For thousands of years, the sun has been the most familiar object in our sky, yet it still holds mysteries we can't explain. What really happens inside its blazing atmosphere? And what could we discover if a spacecraft actually dared to touch the sun itself? You are viewing the closest photographs of the sun ever taken. On Christmas Eve 2024, NASA Parker Solar Probe made history. It became the fastest human-made object ever built, zooming through space at a jaw-dropping 430,000 km or 700,000 km/h. Even more impressively, it flew just 3.88 million mi from the surface of the sun, a distance so small that if Earth and the sun were a foot apart, Parker would have gotten within a half-inch of the star. And now we finally get to see what Parker saw. For the first time, we have direct images of the solar wind and coronal mass ejections captured from right where they begin the outer atmosphere of the sun. The solar wind is a continuous stream of charged particles, mostly electrons and protons, that flows out from the sun corona. As these particles race through space, they carry the sun magnetic field with them, creating a giant magnetic bubble known as the heliosphere. The bubble is like an invisible shield that keeps all the planets in our solar system safe from cancerous cosmic radiation. These stunning images were recorded by an instrument on the spacecraft called WISPR, which stands for Wide Field Imager for Solar Probe. WISPR does not stare straight at the sun. Rather, it records visible light from solar material that explodes away from the sun. During these photographs, Parker was flying in the sun's atmosphere. It was literally skimming the sun. You've probably heard that saying before. Parker touched the sun. But how can a spaceship touch the sun if it's still millions of kilometers away from what we perceive as the surface? The key to understanding what the sun actually is provides the answer. Unlike Earth, the sun has no solid surface. It's a massive ball of hot ionized gas or plasma. What we typically view as the surface of the sun is actually the photosphere, the area where the gas has become dense enough to produce visible light. But this is not a solid boundary. It's more of a fuzzy edge in an ocean of plasma. The sun's atmosphere slowly thins out above the photosphere. There is no definite dividing line, only layers of more and more transparent, lower-density plasma. So when Parker ventured into this outer atmosphere, the corona, it was in a very real sense flying through the sun stuff. The WISPR pictures provide scientists with a closer glance at what occurs to the solar wind just seconds after being discharged from the corona, the outer atmosphere of the solar atmosphere. If you examine the new pictures closely, you will observe something amazing: a sudden collision of three huge solar explosions called coronal mass ejections, or CMEs. They are forceful explosions of solar plasma and magnetic field, propelled into space from the outer atmosphere of the sun. But what is especially interesting is what occurs when several CMEs erupt one after another. They're not solitary events. Sometimes they crash and collide in space, producing much more powerful effects than a single CME in isolation. Knowing how these solar eruptions act and combine is important, particularly because it has a direct impact on us here on Earth. When these intense solar storms hit our planet, they can illuminate the skies with brilliant auroras, even in regions that don't normally have them. But they can also produce severe issues, damaging satellites, interrupting power grids, and exposing astronauts to extreme amounts of radiation. We have already witnessed the effects firsthand. Remember the huge solar storms of May 2024? Those were caused by a chain of eruptions from a very active sunspot area. But what made the storm so incredibly powerful was that three CMEs interacted mid-journey, fusing into what's referred to as a cannibal CME. This combined strong wave battered Earth's magnetic field, generating spectacular auroras around the world, including areas that had never seen them before. This is why Parker's close-up is so significant. By observing these solar events where they begin, we can begin to understand and even eventually be able to predict how space weather could affect life on Earth. Look to the far left of the pictures, and you'll see another interesting feature, an area which designates the heliospheric current sheet. This might sound convoluted, but simply think of it as an enormous invisible building that is key to influencing space weather. To picture it, imagine looking at the sun from the side. The current sheet would look like a giant spinning ballerina skirt curving outward into the solar system. It extends far beyond the planets and encircles the entire sun. But what is it? The heliospheric current sheet is a boundary where the sun's magnetic field changes direction, from pointing north to pointing south. It exists as the spinning sun whips its magnetic field out into space. And this ever-moving sheet is a steadfast component of the solar wind. Why does this matter? Because the current sheet can determine how solar eruptions like CMEs move through space and how intensely they impact Earth. It's one of the most important areas scientists must learn about in order to more accurately predict the impact of solar activity. In 2018, NASA Parker Solar Probe made an unexpected find. It measured bizarre sudden zigzags in the flow of solar wind. These rapid changes, known as switchbacks, looked like the solar wind was folding back on itself in quick bursts, almost like magnetic whiplash. These weren't just isolated blips. Even in Parker's earlier flybys, switchbacks were seen clustering together, hinting that they weren't random. But during the most recent close encounter, scientists noticed something new. The switchbacks were more frequent, more intense, and even better defined. But these aren't just strange solar hiccups. They might hold the key to of the sun's most enduring mysteries: solar physics. The sun's outer atmosphere, the corona, is hotter than its surface. It makes no sense. The corona, extending millions of kilometers from the sun's core, reaches temperatures in excess of 1,000,000 degrees C. That's 200 to 300 times hotter than the photosphere. If switchbacks are caused by energetic magnetic events, such as reconnection, they may be transmitting energy from the surface of the sun outward, contributing to heating the corona to these extreme temperatures. By examining these zigzagging flows up close, Parker may at last help unlock this decades-long puzzle. The Parker Solar Probe is hardly finished. Indeed, its most thrilling phase has only just started. From now until the mission's scheduled conclusion in mid-2026, Parker will make a number of more close flybys of the sun, each one deeper and quicker than the previous. After its last Venus gravity assist in 2024, the spacecraft is irrevocably locked into a record-setting orbit that brings it within one-third the distance between Mercury and the Sun. With each subsequent orbit, Parker will fly through progressively hotter areas of the solar corona, facing increasing temperatures and radiation levels than any other spacecraft to date. Its carbon composite heat shield, previously tested in the December 2024 encounter, will continue to shield its instruments from external temperatures that can reach as high as 1,400 degrees C or 2,600 degrees F. Parker's measurements will be integrated with readings from European Space A's solar orbiter, which orbits further out but carries powerful imaging instruments. Together they provide a 3D picture of solar phenomena. Parker measures from within while Solar Orbiter watches from afar. Like Voyager revealed the edge of the solar system, Parker is revealing its origin. It's a once-in-a-generation mission that is rewriting our textbooks. One question we get asked all the time is, how does the Parker Solar Probe not melt when it dives into the sun atmosphere? It's a good question, and the solution is in some ingenuity brilliant. If Parker is already rewriting what we know about the sun, imagine what it will reveal on its next dive. If you liked our video, please subscribe our channel for more related videos. Thanks.